All right, so for the problem of the day, I wanted you guys to brush up a little on your arrow pushing. This one is a pretty unique reaction. It was actually out of the challenge section of your textbook, and it's relevant to what we're going to be talking about today. So if we look at the starting material and product, they look very, very similar. What this is called is a keto-enol tautomerization. So if we go and we look at the various functional groups in this molecule, we've got this guy. Oh, that was a terrible color. We've got this guy, which is a ketone. And then we've got this alkene with an alcohol. That's called an enol. So this is a keto-enol. It's just our short-term way of saying a ketone next to a double bond that's got an alcohol on it. And essentially all we're doing in this case is moving a hydrogen over to the oxygen that used to be the ketone, and the oxygen that used to be the alcohol now is the ketone. So the first step is to do a proton transfer because we're running this reaction in an acid. I'm going to abbreviate this guy as R, and I'm going to abbreviate this guy as R prime, just so I can avoid drawing a bunch of cyclohexane rings. You guys are welcome to do the same, just as long as you clarify that in your homework. So we'll start with the protonation step. And we've got our hydronium, so this oxygen has a positive charge. First step will be this ketone actually protonating and then kicking off water as your leaving group. I know a lot of people, I was looking at your problem of the days as you were working on them, and you did an addition of a proton to the alkene. That will get you to the right product, but this is actually the preferred mechanism, and I'll talk about that a little bit more when we get further along in the mechanism. So now that we've protonated that ketone, this oxygen has a positive charge. This alcohol over here is neutral. Let me redraw this positive a little bit more clearly. And is oxygen very happy with the positive charge? No. Is there any way we can stabilize it? Resonance, right? So we can push this pi bond up to the oxygen. And if we do that, we can delocalize that positive charge down to the carbon. OH and R prime. Positive charge is now on the carbon. Is there any way to delocalize the positive charge on that carbon? Yeah, resonance. So this is getting back to what we covered last term. We've got to remember that we can delocalize positive charges if there's resonance available. So this becomes an alkene. Now this carbon has the positive charge. Is there any way to delocalize that positive charge? Yeah, push the electrons down from oxygen. So this lone pair can come down, and we get one more resonance structure. And it's important to remember with resonance structures to include a full bracket around it to indicate that it's not that there's one of these existing in solution. It's a hybrid form of all four of them. So it's more of an average view of all of these. Now the next step is we've got water that got kicked off in this first step up above. And this water can act as a weak base. It can come around, grab this proton, kick down electrons, and we can get to our final product. Oop. And so this is an example of the keto-enol tautomerization. The reason that we know the reaction works this way is because if you take a look at this carbon, I'll mark it with black right there. We can look at this using spectrometry, and we can observe that this remains sp2 hybridized during the duration of the reaction. If you do an addition of a proton to the alkene, it actually turns to sp3 hybridized, and that's not observed. So we know that we have to change up our reaction mechanism a little bit. If you did that on the problem of the day, that's fine. I'm more just looking for you guys to try to crack open your book a little bit before class and take a look at these reactions before we dive too deeply into them. Are there any questions with the problem of the day? Kareem?
So I understand it now, but for the electrons that are on the oxygen to begin with, when they come in, is that always the case where they'll always have to beat the double bond?
In this case, yes. We'll cover the acid and base catalyzed tautomerization a little bit further into this chapter. We'll probably cover some of it today. We'll cover that when we get to that section. There's always going to be some caveats in chemistry. All right. So let's go back to our notes that we finished up on yesterday. And we'll come back to this concept of tautomerization a little bit later in this chapter. All right. So yesterday we were talking about hydrohalogenation, and we've already covered hydrohalogenation with alkenes, with double bonds. And we said when we react an alkene with hydrobromic acid, the bromine will add to the Markovnikov side or anti-Markovnikov side? Markovnikov, right? So if we look at the double bond, it's going to add to the more substituted side of that double bond. The same is true with alkynes. So we said we would hypothesize that the more substituted side of the alkyne would be that carbon. We would protonate it, form a vinylic carbocation, and then our bromide would add in, and we would still get this Markovnikov addition to the more substituted side of the triple bond. However, we said that observations don't support this mechanism, and we actually had to come up with a new mechanism that did support this observation. We do know that it forms this product, it just goes through a different mechanism. So the hypothesis that supported the rate analysis said that it was actually a termolecular transition state where you have two equivalents of acid interacting with your alkyne. This bottom equivalent of acid transfers this halide. The top equivalent of acid transfers this proton. And then when they're added in that anti-fashion. So that bottom halide adds to one of those carbons. The proton adds to the other carbon. And then you get anti-addition of your halide and your hydrogen. The reason that this reaction proceeds in this manner is this carbon down here has a partial positive in that transition state, and we know that positive charges can be stabilized through more substitution. So it still works, or we still get the same product that we anticipated, it just doesn't proceed via the same mechanism that we've seen. So make sure that you do remember that hydrohalogenation reactions add anti, and that they add to the more substituted side of our alkyne. It's a little bit confusing because we go through the different mechanism, but the nice thing is the product doesn't really change that much. All right, so let's do an example of this using some real molecules. Let's say we have phenylacetylene. It's an acetylene with a phenyl group on one side and a terminal hydrogen on the other. Let's add hydrobromic acid. Where will the bromine add? Will it add to our red carbon, or will it add to the blue carbon closest to the hydrogen? The red one, right? We know it's going to do Markovnikov addition, so it's going to add to the red one. And we know that it proceeds through that termolecular transition state. So the bromine will add anti to our hydrogen, and the bromine added to the Markovnikov side the hydrogen added anti to the bromine. So we're in good shape. What happens if we react this with another equivalent of hydrobromic acid? What do you guys think will happen? What do you think? Would it rearrange? It'll add to the same spot, right? So last chapter we saw double bonds reacting with halo acids, and we can just do another hydrohalogenation, right? So again, if we compare the Markovnikov to anti-Markovnikov side, we know it's going to add to the Markovnikov side. And if we look at our final product that we get out, we just get a dihalide. Oh man. Br. And if we've got 3 terminal hydrogens coming off the end. So this was a geminal dihalide. Both halogens are coming off of the same carbon. Now, does anybody remember how we can go backwards in this reaction? Go from our geminal dihalide to our alkyne. It's not Le Chatelier's principle. This is what we covered yesterday. We're going to do a double E2 elimination reaction. What reagents do we need in order to do an elimination back to our alkyne? A strong base, right? And so typically the strong base that's used to go backwards is NaNH2. How many equivalents would we need? 2. So we could do 2 equivalents like we saw yesterday. Oftentimes what people will do, because it's very hard to measure out 2 equivalents, is they add in excess and then they add water in. So you can do this, or you can do NaNH2, that's sodium amide, followed by adding in water. I'd be fine with you guys doing either of these. So it behaves pretty similarly to what we saw last term, or last chapter with our alkenes. The question is, can we get anti-Markovnikov addition? So let's take a second and think about that. Oops, anti-Markovnikov addition. If we think back to last chapter, let me move this up. If we wanted an alkene where our halogen added to the less substituted side, what reagents do we need? Peroxide. Exactly. I'm going to move this over. All right, so we need HBr, and we need some sort of peroxide. And when we do this, we're going to add to the anti-Markovnikov side, which we said is that less substituted side in red. The question is, does this work with alkynes? It does. So let's do our same phenylacetylene. Let's highlight our anti-Markovnikov side. So again, it's in red. It's that less substituted side of our alkyne. This time, if we add in hydrobromic acid and our peroxide, we'll get 2 different products out. We'll get one where the bromine adds in a trans manner, and then we'll get one where it adds in the cis manner. In either case, it's important to remember that it's an anti-Markovnikov addition. meaning that we're adding that halogen to the less substituted side of our alkyne. And at this point, we can stop at the double bond, or we can add in more hydrobromic acid and push it even further and get another dihalide. But same rules apply as with chapter 9. We can favor the anti-Markovnikov addition through the addition of peroxides. Yep?
You added more without peroxide to that,
Mm-hmm.
to the Markovnikov side.
Yeah, without peroxides, it would add to the Markovnikov side. Yep. In this case, I mentioned last term, or sorry, I keep on saying last term, last chapter, that we'll discuss this mechanism more in chapter 11. In chapter 11. It goes through a radical mechanism that's a little bit more complicated, but we're going to leave that until chapter 11 for right now. But just remember the anti-Markovnikov addition is favored through the addition of peroxides. Are there any questions on the hydrohalogenation reactions? No? All right, so not to sound like a broken record, but we're essentially going to rehash all of the reactions we covered last term, but with alkynes to see how they vary. Thanks, Adrian. All right, so with our alkene, if we added in a proton source along with water, what would we get out? Would we get a Markovnikov addition or anti-Markovnikov addition? Markovnikov, right? So again, if we look at the more substituted side, we know it should add to that red carbon. So with alkynes, or sorry, with alkenes, you would get an alcohol. All right, so review from chapter 9. Question is, will this work with alkynes? With alkynes, it's a little bit different. So let's say we've got this alkyne. And we add a proton source like sulfuric acid along with water. Our gut intuition would say, well, it should still add to that more substituted side, that red carbon, right? The problem with this is you can try all day long, the reaction will not work. And the reason it doesn't work is because it has a really large activation energy, so large that in order to heat it up to that activation energy, you can bust your molecules and you end up destroying all of your hard work. So we have to insert some sort of catalyst in order to lower the activation energy. So what they found works well is a mercury compound. So we'll still use our proton source and water, but we'll use mercury sulfate. So in this case, mercury sulfate acts as a catalyst, helps lower that activation energy so that we don't have to heat up our reaction as hot and destroy things. And when we do this, we can now add our alcohol to the more substituted side of our alkyne. So now we've got this H3C pointed down. We've got 2 hydrogens added in. And we've got our alcohol. So if we look at this, we've got an alkene, right? The double bond, and we've got an alcohol attached to it. So this is called an enol, just like we saw in our problem of the day. And we saw that enols oftentimes aren't very happy being enols. So if we have more of our acid around, this acid can protonate our alcohol and let's work through the whole mechanism for this. We've got OH2 plus. We've got our 2 hydrogens down here. Now what can we do in order to stabilize that positive charge? Actually, let me change this a little bit. Sorry, I'm going to back up. I'm going out of order here. Let me erase this guy. Sorry. I jumped the gun. I was thinking of another mechanism. All right, in this case, let's actually use our alkene and do the addition reaction to the alkene. Sorry, I know I'm ruining everybody's notes here. In this case, we're going to add our proton to our more substituted side. So this is just like our acid-catalyzed hydration from last chapter. And we've got our CH3 over here, along with our positive charge. Is there any way we can delocalize that positive charge? Bring down electrons from oxygen. Great. So I'm going to slide this down a bit. All right. Here we go. So if we bring down electrons from the oxygen, we can create a resonance structure where now we've got a double bond to this oxygen. We still have our 3 hydrogens. We've got our CH3. And now this oxygen has the positive charge. I know in the example we saw in our problem of the day, the carbonyl acted as the base, but this can also perform a normal addition reaction. Yep?
So would that happen? Because why would oxygen have a positive charge with the carbon?
So remember, this is a hybrid structure. It's not that the oxygen has a positive charge, it's that it's sharing that positive charge along with the carbon. So we have to look at the overall hybrid. All right, now we've also got water around. This water will come, grab this proton, kick electrons back onto that oxygen, and now you've got your final product. So we went from our enol form all the way down to our ketone. So again, this is an example of keto-enol tautomerization. It gets a little bit tricky, but the more you see it, the more intuitive it becomes. Yeah? Yeah, it doesn't stop at the enol. In this case, the reaction prefers to go all the way to the ketone. Let's actually write that down, too, just to make a note of it. So reaction goes to an enol, which then gets tautomerized to the ketone. So just like we saw up here, we go through this enol, where the alcohol adds to the Markovnikov side, but through some proton transfers, we can actually convert it to the ketone form. The ketone form is much more stable.
So is this for every acid-catalyzed hydration?
Yeah, every acid-catalyzed hydration, you end up forming a new carbonyl group instead of an enol. Yep. Raise it up. Is that here? Okay.
Is that you or an N?
The tautomerization, this should be a U. Sorry. The longer you're in school, the worse your handwriting gets. So. All right, let's do some example problems so we can kind of see this reaction as it proceeds. Is it okay if I scroll up? Okay. So let's do this example. And I'm going to draw in all of these methyl groups. just so we can keep track of them. And what we're going to do is our proton source will be sulfuric acid, H2SO4. This will be in water, and then we'll have our mercury sulfate. So let's first try to identify the Markovnikov side. We know we're going to add an alcohol to that red carbon. So let's draw the enol that we get. If we draw our enol, we're going to end up adding a hydrogen there. Oops, sorry, an alcohol. CH3 and CH3. And now we've got two hydrogens over here. So we go through our enol. And we're not quite done at the enol. Yep.
Do you want us to show you the reaction
For this one, don't worry about drawing the reaction. It gets into organometallic chemistry. If you take a graduate level course, you'll see how it works with the mercury. But for right now, just know that you form the enol. Yeah, it's a good question. All right, so now we've got to do the next step. And let's actually work through the whole mechanism, just like we did up above. It's assumed that we have more acid around. So this double bond will attack our acid. When we do that, we've now got 3 hydrogens attached to that one carbon. Our alcohol is right there. And we've got a positive charge on that carbon. Now, I remember when I was an undergraduate, I saw this and I immediately thought, oh, rearrangement. But the reality is that resonance outcompetes the rearrangement. Because it's a true hybrid, there isn't the possibility for a rearrangement reaction to occur. So the next step is going to be these lone pairs dumping down. Let me slide this down a little bit too. And when we do this, we now get our new resonance form. Where this oxygen is now positive. We've got this tert-butyl group coming off of one end. And we've got all 3 hydrogens on the other end. So now we've delocalized that positive charge between that oxygen and the carbon. And then what's the last step? Deprotonation. The step that a lot of people tend to forget about, but is very important. So this oxygen will come, grab that proton, dump electrons down to that oxygen. And we end up with our ketone. So again, this is another example of seeing this keto-enol tautomerization in action. I would recommend trying to practice these in your notebook by hand a few times. They get a little bit tedious, I know. Doing a lot of proton transfers can be tedious, but the more we practice it, the more it will become second nature. All right. The one last thing I wanted to bring up for the, yep. Yeah, if there's a resonance stabilization, that will occur preferentially over a rearrangement, because we know resonance structures are hybrids. It's not that they're flip-flopping, it's a true hybrid form, so a rearrangement won't occur. All right. So there's one disclaimer I'm going to add to this. So I'll add problem/disclaimer. just to make things more fun. What if we have this alkene and we add in our proton source and water along with our mercury sulfate? Which side is our Markovnikov side? They're both the same, right? So in this case, there is not a more substituted side. So this addition doesn't occur preferentially at one carbon over the other. You actually get a mixture of products out where one of them you'll get an addition at one side and the other you'll get addition at the other side. And when you do this, you'll get one where there's a ketone at carbon 2. So if we number our carbons, we've got 1, 2. So our ketone is installed at that second position. Or it can be at position 3. So one thing that hoses up a lot of people is they forget a carbon. So for these reactions, it's a good idea to number them and say, all right, 1, 2, 3, 4, 5. In this one, we're adding a ketone to that 2 position. And in the other one, we're adding the ketone to the 3 position. So you need to watch out for internal alkenes or unsymmetric alkenes. Or sorry, alkynes. Will form a mixture of products. There's really not a good way to prefer one of those carbon positions over the other. So anytime you see an unsymmetric alkyne, you have to watch out for that. The book will occasionally throw these at you to see if you remember. All right, so just like with our hydrohalogenation, we installed that Markovnikov. We have to ask ourselves, is there a way to install an alcohol anti-Markovnikov? What do we use to install an alcohol anti-Markovnikov for alkenes? Hydroboration and peroxides, right? So we have to add some sort of peroxide source. So in this case, there's hydroboration oxidation that can also occur with alkynes. So let's go back and briefly write down the conditions that we used for alkenes. We said in the first step you need BH3, and what was the solvent typically? THF. And then in step 2, what do we need? Peroxides, so normally hydrogen peroxide, and water, or NaOH too. So hydroboration oxidation, we said we'll install at the anti-Markovnikov position, the less substituted side. So if we draw the product that we get out of this, we get an alcohol installed off of that red carbon in the anti-Markovnikov position. So can we do this with alkynes? Yeah. But just like with our acid-catalyzed hydration, we have to watch out for our Keto-enol tautomerization. So let's start with this alkyne. And instead of our typical reagents, I'm going to abbreviate this as R2BH. We normally don't use borane for this reaction, and I'll talk a little bit about that, the reason behind that later on, but it's still a boron reagent that we add in the first step. In the second step, we still add hydrogen peroxide and sodium hydroxide. So very, very similar reaction. If we look at our anti-Markovnikov position, it's on that red carbon again on the less substituted side. So we can immediately say that we've got the alcohol installed there. And does alcohol add syn or anti to the hydrogen? Syn. Just like with our alkenes, these groups have to be on the same side as one another. They both came from the hydroboration step. So right now we've got our enol. And we know that this enol can actually tautomerize back to its ketone. What I'm going to do is we're going to hold off on this mechanism until tomorrow because we're running out of time. But I'll give you guys a preview of your product. What's this new functional group that we have? It's an aldehyde instead of a ketone. So from these reactions, you tend to get aldehydes. All right, so I think we're going to stop there for the day. For the problem of the day, it's going to be one of those problem of the days where you need to pull reactions from the previous chapter, so chapter 9 as well as chapter 10, and it's going to be multiple steps. Try to focus on stereochemistry and make sure that you're doing the correct addition, whether that's syn or anti or Markovnikov or anti-Markovnikov. If you have any questions, feel free to let me know.